So this is a triple integral that we are going to evaluate. Now, what does this mean? Well, a double integral gives us a volume. A single integral gave us an area. So what does a triple integral give us? Well, the problem is it requires four dimensions to really think about. So we can call it a four-dimensional volume or a hypervolume. We are integrating over a region, over a three-dimensional region. So let's describe that region. The order tells me this time z comes first. So z ranges from 0 to 1. So we have planes there. Y comes second. So that's the middle one. Y ranges from 0 to 2. And x is the last one. So x ranges from -1 to 1. So we're integrating over that block. Let's visualize that block. Here it is. And we can take a look at it in our usual orientation. So z is going from 0 to 1. We can kind of see that here. If you want to see the behavior of x and y, let's take a look. Looks like x goes out to 2. Excuse me, x goes from -1 to 1, and y goes from 0 to 2. So indeed, that is our region of integration that we're working with. So the good news is it's really no more difficult to do a triple integral of this form than it was to do a double integral. It just requires one extra step. So we start with the innermost inner integral, which I call III, the innermost inner integral, which is what? Which is this one, the integral as z goes from 0 to 1 of x squared plus y squared plus z squared dz. That is my innermost inner integral. And then what does that become? Well, z is perceived as the variable, so x squared is perceived as a constant. So the antiderivative of x squared would be x squared z, similarly with y squared z. But z is perceived as a variable. The integral of z squared is z cubed over 3, as z ranges from 0 to 1. And then doing that substitution, x squared times 1, z equals 1, plus y squared times 1, z equals 1, plus z cubed over 3, 1 cubed over 3, minus 0 plus 0 plus 0. And my innermost inner integral is simply x squared plus y squared plus 1/3. Notice we have lost the variable. The z is gone. So I'm going to replace that innermost inner integral with what I just did and rewrite it as follows. So replacing the innermost inner integral, we are here, and then our next job is to do what? Is to do the inner integral. So that our inner integral becomes with respect to y, x squared y, because x is perceived as a constant. The integral of y squared with respect to y would be y cubed over 3, plus 1/3 evaluated as y goes from 0 to 2. Small correction, integral of 1/3 is 1/3 y with respect to y. Now plugging in the 2, what do we get? We get x squared times 2, which would be 2x squared, plus 2 cubed over 3, plus 1/3 of 2, minus 0 plus 0 plus 0, so that our inner integral becomes 2x squared plus 8/3 plus 2/3. So we get 2x squared plus 10/3. And then where does this go? Remember, this was the inner integral from here. So replacing that inner integral to get our final integral, the integral will be the integral as x ranges from -1 to 1 of the inner integral 2x squared plus 10/3. So let's quickly do this computation. So the antiderivative with respect to x would be 2x x cubed over 3 plus 10 thirds x, as x ranges from -1 to 1, I believe. Indeed, x goes from -1 to 1. So plugging in 1, what do we get? 2/3 times 1 cubed plus 10 thirds times 1 minus 2/3 times -1 cubed plus 10 thirds times -1. So we have some arithmetic to work on. So we get 2/3 plus 10 thirds minus -2/3 minus 10 thirds. So 4/3 plus 20 thirds, 24 thirds. After all that, the answer is 8. So a little difficult to visualize this, but to think about it, that would be the volume of a four-dimensional figure. So if you had a four-dimensional box, it'd be length times width times height times the fourth dimension, whatever that is. But that's what a triple integral gives us. Our value is 8. And what made this relatively easy was that we integrated this over that box. So the box will be the simplest sort of region I can integrate over.